Yeah, just start reading. So here, this is Riemann's Habilitation Dissertation. This was submitted by him in order to get his, I guess it was his doctorate from Göttingen University. And in the audience was his teacher, his one-time professor, Gauss, who we're currently, the basement project is currently finishing up a 1.5-year long project called Gauss's Mind, of really trying to flesh out exactly what it was and how it was that Gauss thought in order to make the very large number of contributions he made to the theory of mathematical physics, geometry, number theory, etc. And so this is Riemann's writing that got him his doctorate, and where he emancipated man from Euclidean axiomatics.
Riemann on the hypotheses which lie at the foundations of geometry. Plan of investigation. It is well known that geometry presupposes not only the concept of space, but also the first fundamental notions for constructions in space as given in advance. It gives only nominal definitions for them, while the essential means of determining them appear in the form of axioms. The relation of these presuppositions is left in the dark. One sees neither whether and in how far their connection is necessary, nor a priori whether it is possible. From Euclid to Legendre, to name the most renowned of modern writers on geometry, this darkness has been lifted neither by the mathematicians nor by the philosophers who have labored upon it. Move it up. Okay. The reason of this labor has in the fact that the general concept of multiply extended magnitudes, in which spatial magnitudes are comprehended, has not been elaborated at all. Accordingly, I have proposed to myself at first the problem of constructing the concept of a multiply extended magnitude out of general notions of quantity. From this, it will result that a multiply extended magnitude is susceptible of various metric relations, and that space accordingly constitutes only a particular case of a triply extended magnitude. A necessary sequel of this is that the propositions of geometry are not derivable from general concepts of quantity, but that those properties by which space is distinguished from other conceivable triply extended magnitudes can be gathered only from experience. Move up more. There arises from this the problem of searching out the simplest facts by which the metric relations of space can be determined, a problem which in nature of things is not quite definite. For several systems of simple facts can be stated which would suffice for determining the metric relations of space. The most important for present purposes is that laid down for foundations by Euclid. These facts are, like all facts, not necessary but of a merely empirical certainty. They are hypotheses. One may therefore inquire into their probability, which is truly very within the bounds of observation, and thereafter decide concerning the admissibility of protracting them outside the limits of observation, not only toward the immeasurably large, but also toward the immeasurably small.
All right, so that's his opening statement, which, depending, people can. Well, as people tell people now, one element of this is that. First, just for people, so you know, if you want to get this, you can go to the WLYM site and click on this one part that says, underneath the pictures of the various projects we're working on, there's something that says, yeah, multimedia archives or something like that. If you click on that and then go, then a page will go on the left column and click the old site, and that'll take you to the old site, which people are probably familiar with. And then on there, you just click on the classics in the right-hand column, and then under Riemann, this paper's there. Just so people, it's worthwhile reading through this a number of times to find the profundity of what he's saying. But recognize that prior to this, no one had explicitly put forward the idea that you could challenge the axioms of Euclidean space-time. That though implicitly people like Gauss or Kästner before him challenged it in various ways, the idea that someone would come forward and just state in principle that we don't necessarily have to accept the geometric relations of Euclid and the system of Euclid was a real revolution for science. And in fact, it was a revolution in terms of epistemology, which created a sweep of scientific development which is unprecedented in human history. I mean, if you just think about, say, even the period leading up to, you can just take from, say, the American Revolution up till, just say, 200 years, 1776 to 1976. And think about the density of discoveries and breakthroughs that have been made. I mean, in 1776, people were still horse and buggying it, right? I mean, it was pretty bad. You're lighting candles, you're riding horse and buggy, etc. To within, the 200-year period, we're going to steam engines, to internal combustion engines, to then with Riemann and what he had introduced epistemologically, you then had the potential for, towards the end of World War I, the breaking of the sound barrier, transonic flight, where we took to the skies. And then, 30 plus years beyond that, we were putting a human being on the moon. We were engaged in space travel. So in just that 200 years, and then the thing really sort of went hyperbolic with the revolution of Riemann. I mean, we went from literally, living in the dirt to putting a man on the moon. Counterpose that 200-year interval to, say, 1,500 years prior to that. Not a lot had changed scientifically. I mean, you had certain breakthroughs, obviously kicked off by Cusa with the in the 1400s and leading into the Italian Renaissance. But that sweep, there's a reason why LaRouche often looks at that and then counterposes that period to the growth of population, where you had unprecedented growth in discoveries, in population, in scientific advancement, etc. But if you look at this period, from the time around the time of the death of Lincoln, who died in 65, Riemann died in 1866. And if you look at that period, from around the late 1860s, this sort of what led into the 1876 convention, and you look at that really less than 60-year sweep up to the period of Einstein, you had a tremendous amount of breakthroughs and developments occurring in the world. From things like transonic flight to really what you had culminating with people like Einstein, which was breakthroughs in the very small, at the subatomic level, with the discovery of the ability to harness nuclear processes, nuclear power, fission, and ultimately this was leading into fusion, which was then the combining of nuclei, essentially. But what you have to understand was that it was because of what Riemann had put forward here that made all of that possible. As he states here, that though what we perceive as Euclidean a Euclidean type space may seem legitimate empirically, if we just observe things sort of in a simple empirical state, there's no reason to assume that those axioms hold as we go into the very large and then into the very small. Right? Just because, obviously one of the common ones about, only one line, there's only one line, one shortest line that can pass between any 2 points in space, that necessarily holds in the immeasurably large or the innumerably small. And it was in fact an insight into questioning the shape of space in the very small that led to the breakthroughs of people like Einstein in his, what he developed out of his relativity theory, and then what he led to his theoretical ideas that then led to the experiments and the breakthroughs in nuclear physics and the splitting of the atom. Something we can do is just, I sort of excerpted certain elements of this that we can read through. Just this part here and then the last section. And let's give you a sense of kind of where Riemann was pointing. And then we can sort of take a look at that and then look at what Einstein actually did. And hopefully you'll be able to see the sort of parallels in what Riemann had kicked off and how it was realized and developed by people like Einstein. So if you want to keep reading along there.
Section 1, the concept of Enfold extended manifold. While I now attempt in the first place to solve the first of these problems, the development of the concept of manifolds multiply extended, I think myself the more entitled to ask considerate judgment, inasmuch as I have had little practice in such matters of a philosophical nature, where the difficulties lies more in the concepts than in the construction, and because I have not been able to make use of any preliminary studies whatever aside from some very brief hints which Privy Councillor Gauss has given on the subject in his second essay on biquadratic residues and in his Jubilee booklet, and some philosophical investigations of Herbart.
All right, so then section 1 and 2, Riemann goes through a kind of a geometric investigation of manifolds. A manifold being a multi-dimensional construct. Space as being one of them. Right? Our ideas of space of forward, back, up, down, left, right, that constitutes a triply extended manifold. There's three degrees of movement, so to speak. And what he takes up is, do we necessarily, or should we necessarily assume that triply extended manifold is of a Euclidean type? Could it not be that space is different than of a Euclidean type? Should we necessarily assume that because it looks as if the shortest distance between myself and Torin is what we would call a straight line, in the empty box sense of a straight line, a linearized idea of a straight line, should we necessarily assume that that's the case? And, Einstein takes this idea up. That, well, you can do sort of a mental trick. Maybe this will give an idea of some of what.
Before you do that, can you just briefly elaborate what you mean by Euclidean?
Well, Euclidean is one of the fundamental postulates of Euclidean geometry is first to assume that you have such things as that that the universe as a whole, that space is flat in 3 dimensions. That first what's assumed is sort of an idea which can be played in the mind. That if we were to remove everything out of this room, remove the room, remove the building, remove the planet Earth, remove all the stars, remove everything that we consider as stuff, material in the universe, from the universe, what we would be left with is effectively an empty box, infinitely extended in 3 directions, where something that was set in motion, and one thing were then put in there and set in motion in any one direction, it would continue to infinity in a straight line in that direction. From that sort of, and this is something that Kant also developed, this idea that is sort of a pre-established notion in the mind of man. That man is born with that inherent axiom about the nature of space. That space and time are separate, and that space ultimately, when all material is removed, is a 3-dimensional, flat, infinitely extended entity, so to speak. And then within that, what Euclid's developing is that given any 2 points which have no depth, no width, no dimensionality to them, but between these dimensionless points, the shortest distance is a straight line. And that 2 straight lines that are parallel to each other, meaning that a third line, for example, would intersect both of them at 90 degrees, that if these are allowed to extend forever, they would extend to infinity and they would never meet. They would remain parallel to infinity, never meeting. So certain mental constructs based off a certain assumption about the nature of space and time. And this is what Riemann challenges, and Einstein has certain ways of challenging it as well. I mean, one way you can think about it is that a lot of this comes from assuming that what we perceive can be then projected onto reality as reality. Like, for example, if I'm looking across this table and I set up 3 cups, all of equal size along this table, and I'm looking here at them. If they're all on this plane, I would say that they all lie on a flat, straight surface, right? If I know they're all of equal size, if I've put them together one time, so okay, they're all of equal size, and I line them up and look straight across, and don't see any kind of variation in height amongst them, I would say, okay, well, we can assume that they all lie on a rigid surface which is flat. Right? And we would perceive them with light reflecting off them. We make a certain... And from this we could come up with some generalized concept of what we consider flat. And then we would develop a geometry which holds according to these kind of constructs, of points along this flat surface. Right? These could be replaced then by points, and our idea of what straight is relative to that. But, one thing what Einstein starts looking at in relativity is what if in fact, now if we had something like this, some kind of curved, I have my cups on some kind of a curved surface here. Right, I'm looking at it. My eyeball here. Now we might assume that, well, I wouldn't be able to see one of them. I know there's 3 cups. I can see over the top of one of them, and I can see another one behind it. And I can't see, a third one. I might say, okay, well, they must obviously be located on some sort of a curved surface, right? The way they're lining up, I know they're all of equal size, but what I'm seeing is something other than what I would assume I would see if they're on what I've determined to be a flat surface. But what if the light that's required for me to see these cups itself is in fact bent by its relationship to the surface? What if the shape of the space that the light is traveling in fact travels along lines which are of the same curvature, so to speak, as the space in which I'm observing these cups? Would I be able to conclude anything other than that these cups are all in a straight line? Wouldn't my eye perceive the same phenomena as we assume to perceive whenever we see 3 cups lined up on a desk here or something?
Perspective-wise, I'm not imagining that this is there.
Because you see, because light is reflecting off something and making its way to your eye, right? And the reason why, say, in what you think in your mind's eye now, if you had 3 cups on a hill like this, you would think, well, you wouldn't see this one. You would see this one higher than this one, right? Because you're assuming that the light is traveling in straight lines, emanating in all directions at your eye, so you're not going to even see this one, right? The light is just traveling in straight lines. So you're going to see this one here, you're going to see this one higher, and you're not going to see this one at all. But what if, in fact, the light that reaches your eye is itself being bent with the same curvature that the so-called hill has, or the curved surface has?
Then wouldn't you see the
Right. That the light here is not just going off in straight lines, but the light that's, say, hitting this cup is hitting it and reflecting in a bent way.
Yeah, theoretically, but that never happens.
Are you suggesting the possibility through the desire, or are you just saying one day possibly light could bend like that?
Well, I'm saying
the desire is there, the consciousness will allow it.
Well, I'm saying, do you know what path light travels?
I believe it's limitless.
I'm saying, do you know whether or not light bends, or is it always going straight lines?
I'm not gonna. What I know, light travels in straight lines, but I'm not limited to that fact. It's just my experience. And light kind of emanates too. Light can pierce through certain things, so light can travel through certain objects. Therefore, maybe it can travel around certain objects. I don't know. We're saying, if the idea is there, then the ability is there. Possibility. If
you were here observing these 3 cups and light was being bent, was bending with the same degree of curvature as, say, the hill that those cups were sitting on, wouldn't you perceive the same thing as you assume you perceive now when you look at 3 cups along a straight, flat surface?
Just have to do the experiment. I'm not sure. Like he's saying, in theory, yeah, you would see all 3 cups. If the light's bending and your eyes
beam of light. Well, my question is then, whenever you, right now, look at a flat surface and see three cups and have them lined up and say, okay, that's flat, how do you necessarily know that you're not actually looking at this and perceiving it as this?
Reality's a clever trick. I don't know.
Well, that's the kind of thing that Riemann and Einstein were posing. Why assume that because things are perceived in a way that you construct in Euclidean way, why assume that that is actually the shape of the space that you're existing in?
Could you use as another example the fact that the Earth itself is round? However, if we took like a T-bar or any type of object which we measure the straightness of a surface itself, even though the Earth is round, the T-bar would say that it's straight, and everything we perceive about the Earth seems to say that it's straight, but it's round in fact. Could you use that as another example?
You could maybe use that as a metaphor. I don't know if that would be an example, a principled example, in the sense that you're not. I don't know if you're necessarily seeing a paradox that's a result of a physical principle, or if it's just something that's seems to be paradoxical, if you know what I'm saying. I'm saying in this case here, you're observing a phenomenon that you're assuming has this relationship. But if you were able to sort of get outside the process, you'd be able to see that in fact what's actually occurring is that you're dealing with a curved, you're dealing with light being bent according to a curvature in which your cups are being situated. So that what's perceived is this. You're perceiving, you have no way of, in terms of your perception of this phenomenon, of distinguishing between what you're seeing and a mental construct which is of this quality. But you might find that if you then extend the process further, there's certain things that should occur in a geometry according to a Euclidean one, in fact, break down in this geometry. You know, one of the popular ones is that, you know, if you look on a sphere, two great circles two lines at this moment, these two lines will intersect this third line at right angles. And by definition, will be considered parallel. But as you extend them further and further, in fact, they meet at the pole, which is a result of the fact that you're not dealing with simply a flat space, you're dealing with a curved space, a spherical space. And so these are the kind of geometric paradoxes that Riemann was investigating and putting forward. Saying that we can't assume, as he says, that the axioms that we generate from experience, those being a sort of Euclidean axioms of experience in terms of the shape of space, we can't necessarily assume that those axioms hold true whenever we extend our domain into the very large and the very small. You know, for example, I mean, you get certain phenomena like this, like, you know, people know that two like-charged things, so you have two magnets, right? You have two like charges that their power of repulsion will increase an inverse square to their distance. So in other words, as they get closer and closer and closer, their force of repulsion is increasing. And it would grow at a parabolic rate. So if this was measuring, if this curve was measuring repulsion, all right, so upwards direction is measuring repulsion, and this is this would be distance here. So as they get closer and closer and closer, their force of repulsion is increasing, increasing, increasing. Except that at a certain point, this curve spikes down like this, and a different force takes over, and they actually bind together. And this is what's, this crosses what's known as the Coulomb Barrier. So if you had two, say, like charged particles, right, and just imagine you had them, you're holding your repulsion is more and more and more and more, but at a certain point, the process inverts, and no longer is there a repulsion, but the thing's actually now a very strong force takes over, and they become bound. So this is an example of the kind of idea that, certain kinds of assumptions about how things relate to each other in space-time, which we observe in the domain of the visually observable, or what we might assume to be the domain of the visually observable, cannot necessarily be assumed to hold as you move into the very small as well as into the very large. And as in fact, these are the kind of things that led to the breakthroughs in effect, freeing man of a limited thinking of a Euclidean type. Riemann was able to free science from the adherence to Euclidean set of axioms and ideals, saying, well, okay, whatever we observe, we have to somehow figure out a way that it fits and makes sense according to a Euclidean notion of space-time. So why don't we just read on more of what
Cody,
yeah
the last example, does
Yeah.
it have something to do with the nuclear reaction of a sort?
Yeah, because that's that's the thing. Whenever you're dealing with a nucleus, the protons, you're dealing with a bunch of light-charged particles, which are somehow maintaining a very close relationship to each other. Now, our empirical experience up to the point when they started to realize this seemed to contradict that. We found that light charges will tend to repel, and different ones will be the ones that come together. But as we move into the very small, different forces seem to be operating. There's a different curvature to the space in the very small. And likewise, there perhaps a very different curvature to the space in the very large, beyond what we assume to be the nature of space and time and the immediately observable. Einstein also found this to be the case whenever this is the whole idea of relativity, that once space and time are bound, and that in fact, as you approach certain limiting velocities, namely the speed of light, that space and time begin to be contracted. That it's not an absolute phenomenon. And that in fact the kind of contracting or bending of space-time is what we know is the kind of phenomenon that we observe with gravitation. That in fact gravitation is a bending of space-time. Now, one of perhaps the epistemological flaws that you've got with Einstein, and it's maybe it's just the way he expressed it. It's not clear exactly how he thought about it, but it's often expressed that it's matter which bends space-time, which is why, for example, people have seen maybe some of these models that are used where they get like a big piece of like spandex material or something that's stretched out and it's very flat. But if you put a bowling ball in it, it's going to bend the material. And that's used as a sort of heuristic about the bending of space-time. This is what you get with, say, with planets, which is what, and Einstein equated the idea of gravitation, the effects of gravitation, to what you'd experience as acceleration, which is why, for example, objects will accelerate as they approach the Earth. As a very small object approaches a very large one, under the influence of gravity, it's going to accelerate. It's going to be an acceleration, which is going to be, the rate of acceleration is going to be a function of the amount of curvature of the space-time, which he would say is a function of the mass of the object which is bending the space-time. Now, Kepler, LaRouche, others would actually invert the way of thinking about it. That in fact it's the curvature of space-time which is generating the effect that we know as matter. That perhaps the Earth, what we know as sort of material objects in space, are really just sort of singularities as a function of the curvature of space-time, where what's primary is the curvature of space-time, not the object. Whereas what you could interpret perhaps from what Einstein was saying was that the object is primary and that's what's bending space-time. So there's a certain, what might seem a minor, but has a very profound epistemological difference to it. Though, it's hard to say exactly what Einstein really thought. He might actually agree with LaRouche's notion on this. But here, let's take a look at a continuation of what... remember, this is stuff Riemann was writing and discussing all this stuff long before the breakthroughs were made about the nature of space-time into very small. So he's hypothesizing about where new breakthroughs might occur and what they might be. Just as he had forecast prior to its occurrence the formation of shock waves in transonic flight. That as a body moved faster and faster, you had a tighter compression of air or sound waves in air, that you would reach a certain limiting point at which the object would move faster than the propagation of the air in front of it. And you get a kind of a shock front formation. And this is long before the actual physical demonstration of the truth of that, with the sonic boom and what we know as transonic flight. So here, this is the last part of Riemann's paper, where he kind of gets into some of the theoretical directions that this may be leading science. So if you want to...
Section 3, Application to Space. Following these investigations concerning the mode of fixing metric relations in an Enfold extended magnitude, the conditions can now be stated which are sufficient and necessary for determining metric relations in space, when it is assumed in advance that lines are independent of position, and that the linear element is representable by the square root of its differential expression of the second degree. That is, if flatness in smallest parts is assumed. Move it up. These conditions, in the first place, can be expressed thus: that the measure of the curvature in every point is equal to 0 in 3 directions of surface, and therefore
the metric relations of the space are determined when the sum of the angles in a triangle is everywhere equal to 2 right angles. In the second place, if one assumes at the start, like Euclid, an existence independent of situation, not only for lines but also for bodies, then it follows that the measure of curvature is everywhere constant. And then the sum of the angles in all triangles is determined as soon as it is fixed for one triangle. In the third place, finally, instead of assuming the length of lines to be independent of place and direction, one might even assume their length and direction to be independent of place. Upon this understanding, the changes in place or differences in position are complex quantities expressible in 3 independent units. In the course of the preceding discussions, in the first place, relations of extension, or of domain, were distinguished from those of measurement, and it was found that different relations of measure were conceivable along with identical relations of extension. Then were sought systems of simple determinations of measure by means of which the metric relations of space are completely determined and of which all theorems about such relations are a necessary consequence. It remains now to examine the question how, in what degree, and to what extent these assumptions are guaranteed by experience. In this connection, there subsists an essential difference between mere relations of extension and those of measurement. In the former, where the possible cases form a discrete manifold, the declarations of experience are indeed never quite sure, but they are not lacking in exactness, while in the latter, where possible cases form a continuum, every determination based on experience remains always inexact, be the probability that it is nearly correct ever so great. This antithesis becomes important when these empirical determinations are extended beyond the limits of observation into the immeasurably great and immeasurably small. For the second kind of relations obviously might become ever more inexact beyond the bounds of observation, but not so the first kind. When constructions in space are extended into the immeasurably great, unlimitedness must be distinguished from infiniteness. The one belongs to relations of extension, the other to those of measure. That space is an unlimited, triply extended manifold is an assumption applied in every conception of the external world. But by it, at every moment, the domain of real perceptions is supplemented and the possible locations of an object that is sought for are constructed. And in these applications, the assumption is continually being verified. The unlimitedness of space has therefore a greater certainty, empirically, than any experience of the external. From this, however, follows in no wise its infiniteness, but on the contrary, space would necessarily be finite if one assumes that bodies are independent of situation, and so ascribes to space a constant measure of curvature, provided this measure of curvature had any possible value, however small. Positive value. Right. If one were to prolong the elements of direction that lie in any element of surface to shortest lines, geodetics, one would obtain an unlimited surface with constant positive measure of curvature. Consequently, a surface which would take on is that in a triply extended manifold, the form of a spherical surface, and would therefore be finite.
Hey, Cody.
Yeah.
Do you think you could move the window a little bit to the right from our point of view?
Yeah.
Because it'll be easier for Delonte to read. This guy here. Then you can stretch it out.
Questions concerning the immeasurably large are, for the explanation of nature, useless questions. Quite otherwise is it, however, with questions concerning the immeasurably small. Knowledge of the causal connection of phenomena is based essentially upon the precision with which we follow them down into the infinitely small. The progress of recent centuries in knowledge of the mechanism of nature has come about almost solely by the exactness of the synthesis rendered possible by the invention of analysis of the infinite and by the simple fundamental concepts devised by Archimedes, Galileo, and Newton, and effectively employed by modern physics. In the natural sciences, however, where simple fundamental concepts are still lacking for such synthesis, one pursues phenomena into the spatially small in order to perceive causal connections, just as far as the microscope permits. Questions concerning spatial relations of measure in the indefinitely small are therefore not useless. If one premise that bodies exist independently of position, then the measure of curvature is everywhere constant. Then from the astronomical measurements, it follows that it cannot differ from zero. At any rate, its reciprocal value would have to be a surface in comparison with which the region accessible to our telescopes would vanish. If, however, bodies have no such non-dependence upon position, then one cannot conclude to relations of measure in the indefinitely small from those in the large. In that case, the curvature can have at every point arbitrary values in three directions, provided only the total curvature of every metric portion of space be not appreciably different from zero. Even greater complications may arise in case the line element is not representable, as has been premised by the square root of a differential expression of the second degree. Now, however, the empirical notions on which spatial measurements are based appear to lose their validity when applied to the indefinitely small, namely the concept of a fixed body and that of a light ray. Accordingly, it is entirely conceivable that in the indefinitely small, the spatial relations of size are not in accord with the postulates of geometry, and one would indeed be forced to this assumption as soon as it would permit a simpler explanation of the phenomenon. The question of the validity of the postulates of geometry in the indefinitely small is involved in the question concerning the ultimate basis of relations of size and space. In connection with this question, which may well be assigned to the philosophy of space, the above remark is applicable, namely that while in a discrete manifold the principle of metric relations is implicit in the notion of this manifold, it must come from somewhere else in the case of continuous manifold. Either then the actual things forming the groundwork of a space must constitute a discrete manifold, or else the basis of metric relations must be sought for outside that actuality, and colligating forces that operate upon it. A decision upon these questions can be found only by starting from the structure of phenomena that has been approved in experience hitherto, for which Newton laid the foundation, and by modifying this structure gradually under the compulsion of facts which it cannot explain. Such investigations as start out, like this present one, from general notions can promote only the purpose that this task shall not be hindered by too restricted conceptions, and that progress in perceiving the connection of things should not be obstructed by the prejudices of tradition. This path leads out into the domain of another science, into the realm of physics, into which the nature of this present occasion forbids us to penetrate.
And so that's how his dissertation ends. So you can see, he's making very much some of the obvious point, right? That we can't allow ourselves to be limited by the prejudices of the traditions, namely that of Euclidean geometry and other axiomatic assumptions. And that this would then be the gateway into new breakthroughs in the domain of physics, which, in fact, it was. Now, I do time because certain things we'll pass up. And one thing I would suggest to people, and actually Chase and I have talked about doing a class here in the near future, more going through sort of fleshing out Einstein's work on relativity, give people a sense of that and some of maybe where that led into the problems of quantum mechanics. So we can save those details for later. One thing I would suggest is that you can find this, a paper written by Einstein called Geometry and Experience, which he developed, it says, an expanded form of an address to the Prussian Academy of Science in Berlin on January 27, 1921. If you go, it's pretty easy to find on the internet. This is called Geometry and Experience. And if you look that up, you'll see the influence of Riemann is very, very clear. At the end, he goes through some of his simple pedagogy in looking at projective geometry, where he's looking at if you were to have a spherical surface with, say, circles on it, and on the surface itself, you could move these circles around anywhere you wanted to, and they, without distorting the circles. But they were bound by that. They were, in effect, bound by the fact that they were on a circle, but they were unbound by the fact that there's nowhere, you would never reach a point where you couldn't continue to move it. So it was limited in that it was limited by the geometry of the sphere, but it was unbound in the sense that there was no place where you would run into a boundary at which you cannot continue to move it. And he says, but now what if you were to project those circles onto a flat plane? That you would see distortions. That as the circles move more towards the pole, towards the light, you would get distortions of the circle to where, part of the circle would stretch into an ellipse, or at certain points the top of the circle would blow up to infinity. You'd no longer have curvature there. And he says, so that would be the actuality of the space that the circles were existing on was on the spherical space. But the perceived space of the flat plane would give you a different kind of picture. And then he says, but what if now the metric that you use for measuring on the flat plane itself was subjected to the same deformations as the shadows? So that as far as you could tell, your measuring rods, so to speak, and the shadows were all subject to the same deformations as a result of the projection. You, in effect, would not necessarily be able to... You'd have a tough time determining exactly what kind of surface you were dealing with, but you would not be... You could not necessarily say that the deformations were variations from what you would otherwise assumed to be linear metric relationships as measured by your measuring rod. In a sense that, like, for example, if your measuring rod itself were to stretch as the shadows also stretched, even though from, say, an outsider perspective, as you moved 1, 2, 3, 4, 5 towards, say, the stretching direction, you would say, well, this thing is obviously getting longer. What was 1 here is clearly not the same length up here. From your vantage point on the surface, 1 here would not be unknowable as any different than 1 up here. Because on the surface, it's all just, your metric is also changing in accordance with the surface itself. So he's posing the question, what if your metric is itself susceptible to the same transformations as the space in which you're measuring things? Now, it sort of throws into question, the way we assume that we can sort of project certain kinds of constructs about space and time onto physical reality. Now, we can assume that we can measure reality according to some construct of the mind about length, time, space, etc. But what if the actual metric you're using to measure time and space are susceptible to the same transformations as all other actions within that space and time? How do you actually start to determine exactly what the true curvature, the true shape of the space and time in which you exist is? And so anyway, he takes up a lot of this stuff, and he makes very clear reference to Riemann in particular, and he raises the question about whether or not, the exact same question, about whether or not we can assume the axioms of Euclidean geometry, or if in fact we live in a Riemannian geometry. And so, that's the point of the whole paper. It's worth, he says, for example, the question whether the structure of this continuum is Euclidean or in accordance with Riemann's general scheme or otherwise is, according to the view which we here begin advocated, properly speaking, a physical question which must be answered by experience and not a question of mere convention to be selected on practical grounds. Riemann's geometry will be the right thing if the laws of disposition of practically rigid bodies are transformable into those of the bodies of Euclidean geometry with an exactitude which increases in proportion as the dimensions of the part of space-time under consideration are diminished. And, he goes on into, he brings up specifically certain breakthroughs he had in relativity, etc. So in applying very directly Riemann's method and continuing this arc of development that was instigated by Riemann, who himself was acting in a tradition of people like Kepler, Fermat, Cusa, and Gauss, Einstein was able to unleash, and make certain fundamental discoveries which transformed then man's relationship to the universe. Namely, one that we all know of, nuclear power. Right? That potential to unleash a new power to man that will allow us to support ever more people at ever increasing standards of living with ever increasing numbers. And so he definitely represents a certain continuation of this arc. Now, the thing to look at is that there were a couple of other contemporaries of his who also represented this, and we don't have time to get into them. One being Vladimir Vernadsky, who really introduced this idea of the biosphere and the noosphere, to really now pose the question about whether or not there was simply one space, not just whether or not space was curved or not curved, etc., but in fact, are there more than one spaces? In the sense that you've got an interaction of different domains, namely the biotic, the abiotic, which is the non-living, the biotic, which is the living, and the noetic, which is the cognitive, the domain of human cognitive ideas. That in fact you had three different types of space constantly interacting, which would themselves, depending on which space was, I guess, principally acting at any moment, would determine the characteristics of action in that space. You know, the different molecules, for example, would act differently depending on whether or not they were operating in a biological process or in a non-biological process, or whether or not they're acting under the influence of a cognitive process. You had also a contemporary, and Vernadsky himself also references Riemann and the necessity to utilize Riemannian geometry and trying to understand the type of space characterized by living phenomenon. Now, he, like Einstein, had a certain problem in that they had a sort of a formalistic idea about what Riemann was getting at. Perhaps no fault of their own, but I think probably Vernadsky was somewhat dependent on interpretations given to him by collaborators, mathematicians, and others who perhaps presented it in certain formal terms, but which he tried his best to apply, because he realized that also, and he says explicitly, Euclidean space is not properly applicable to living space, to the kind of phenomena that occur in a living process or in a domain characterized by living activity. Also, you had a guy, Max Planck, who made certain breakthroughs at the subatomic level about harmonic relationships at the subatomic level. That you get certain kinds of discrete expressions in the subatomic domain. That, for example, the kind of light being emitted from whenever you excite a particle, a gas or something, that you get discrete readings of light emissions from particles. That it's not continuous. Even if you say continually increase the amount of energy into a process, the resulting effect is not going to be a corresponding linear increase. That in fact you're going to get discrete effects, which often expressed as spectral lines whenever you do like these color spectrosity of gases, etc. And so he developed an idea of a certain kind of quantization of space. That space has a harmonic character to it. That it will express itself at certain harmonic intervals in a continuous process. And so these three guys who were contributing profoundly in various domains of science, who very explicitly and epistemologically embodied these ideas and these ideals of Riemann, who are really pushing the ideas of Riemann, the breakthroughs of Riemann forward. Now, the interesting thing is that all three of them died within about a 10-year span of the death of Roosevelt. That you had Roosevelt died in 1945, Vernadsky died also in 1945, Einstein died in 1955, and Planck died in 1947. So coincident with the death of Roosevelt was also the death of the last dinosaurs, or the last vestiges of the Riemann tradition in science. And I don't think it's coincidence that that tradition was not really picked up or continued in the way that it could have been had Roosevelt lived and had his policies lived. That, in other words, if you think about the kind of, the ideas that LaRouche develops in economics, right? There's a very intimate relationship between economics and economic policy and science and culture. That they exist in a very dynamic way with each other. That with the death of Roosevelt and the death of this idea of ending colonialism, of developing the world, of expanding populations, in a sense the necessity to produce the kind of scientists and to make the kind of breakthroughs to realize that political and economic intention was not there. And so therefore the vectoring in the scientific institutions was not there to promote that tradition. And if the overall policy is going to be of oligarchism, well then your science can be bastardized. The necessity to pick up a tradition which would allow for development in the sciences to facilitate the want of growth of nations and people is not there. And in fact, what we have in this, we can just conclude with the flip side. We'll see what actually happened. And we can view this through the words of Bertrand Russell.
Hey Cody, you know what they died from?
All their cause of death?
No, I don't. Not off the top of my head. Tuberculosis.
Right.
Did Max Planck go like crazy?
He was attacked. I don't know exactly. That is some of the stuff that we're going to be getting into with the next basement project. But here's, like we said, what you had with relativity, what Einstein had developed with relativity, and it should be noted, this guy we're talking about, for those who know, Bertrand Russell, this is not just some nut off the street. Right? You can find any crazy person off the street who says all kind of wild things. Doesn't necessarily mean that they're a threat to the existence of humanity. But when you have someone whose great-grandfather was a former Prime Minister of England, who sat at the table with the leading policy figures of the 20th century, who was considered a towering intellect on the campuses, who had access to the highest levels of power, and who was influential in that, well, then you see the real why LaRouche at one point considered Bertrand Russell to be the most evil man of the 20th century. And here you get a sense. This first quote is a quote from Russell in his the way that he would spin the breakthroughs of Einstein about relativity. Right? Because what Einstein showed was that there is no such thing as a certain absolute space-time. That space and time can change, can bend, depending on your frame of reference. Now, the irony is that he said that the thing that is constant are universal principles. That what we experience, it's really what we are discussing, that the assumptions of Euclidean geometry and infinite extension, etc., go out the window. But what we have to try and find is the higher universals that are determining the characteristics of space-time. But instead, here's how Russell twists it. He says, causation, in the old sense, no longer has a place in theoretical physics. The collapse of the notion of one all-embracing time, in which all events can be dated, must, in the long run, affect our views as to cause and effect, evolution, and many other matters. For instance, the question whether, on the whole, there is progress in the universe may depend upon our choice of measuring of time. If we choose one out of a number of equally good clocks, we may find that the universe is progressing as fast as the most optimistic American thinks it is. If we choose another equally good clock, we may find that the universe is going from bad to worse, as fast as the most melancholy Slav could imagine. Thus, optimism and pessimism are neither true nor false, but depend upon the choice of clocks. So you start to see, obviously, where he wants to take this thing. Now, it should be noted that Einstein was the first person who published his works was Russell. Now, there's a real attempt to usurp and use Einstein to further sort of stamp the oligarchical mindset onto the world. To really move, to sort of take what had been developing and to reverse it back to the era of relativism, radical positivism, the ideas of entropy, purposelessness, etc.
Cody?
Yeah.
What was Einstein's opinion about Russell? Like, personal opinion?
I don't know. I mean, Einstein's one of these kind of funny dudes where I think he wasn't always totally aware of what was going on around him. I mean, on one level, he fell into the trap in believing that Russell was a pacifist.
Yeah, because he has a document, I don't know if it's overtly, but it's somewhat praising Russell.
Yeah. Now, he would challenge his scientific beliefs, but it's sort of become academic. He clearly did not see that Russell was the most evil man of the 20th century. Now, here's what he has to say about breakthroughs that were made in quantum physics, which just briefly, and this is something that we'll get into when Chase and I do this class, is that depending on which experiment you conduct in looking at quantum phenomena, in looking at, say, the movement of alpha particles or beta particles, photons, light, really, even light emissions. It will tend to express itself sometimes as a particle, other times as a wave. Certain experiments show the kind of effect you get whenever you shine light through two slits. People may have done this. If you shine light through very thin slits, that the light doesn't just hit the slits and then come out on the other end as two just thin lines, but hits the slits and then it re-propagates in a wave form, and you get certain interference patterns on the wall, right? Photons, when photons, or you might have, I don't want to use particles, are shot at slits, you'll get the same kind of effect. They'll distribute themselves on, say, a photo plate in ways which would tend to indicate that they're wave phenomena, that light is a non-material kind of wave phenomenon. But other experiments will show a distribution of photons or subatomic particles, what have you, that will indicate that they actually behave more like a particle, like a discrete element, like a rock or something. And depending on which experiment you use, the same stream of photons will express itself in two completely, seemingly contradictory ways. Now, one of the things that comes up is that you can never, when it comes to that, you can never actually know both the position and the momentum of a subatomic particle. One, because to observe something, you have to interact with it using some sort of electromagnetic phenomena, whether it be light or something, right? To observe something, whether it be with an instrument or with your eye or whatever, you have to interact with it. Now, like when I observed Delante here, there's some interaction in terms of there's light, which is an electromagnetic effect, hitting him, radiating off him, and then hitting my eye, and I'm registering, the phenomenon of Delante sitting here. When you're dealing with the effect of light on him, my perception is negligible, right? It doesn't change if I can locate where he actually is or not. But at the subatomic, light hitting an object is going to add energy to that object. Is going to change perhaps its direction, its velocity. So if I interact with it, I could maybe locate its position, but I can't actually say what direction it's going in, or its momentum. If I measure its momentum, I can't actually determine exactly where it is. I can only determine a sort of what would be its statistical distribution that it might have according to certain wave phenomena, wave propagation, etc. So there's this, this is the so-called duality at the subatomic. Now, better scientists see this as an opportunity. Okay, there's something paradoxical here. We need to figure out what's actually happening. There's some higher principle operating that we've yet to grasp, which is expressing itself in this particular paradoxical way. Others use it as justification to say, well, this means that fundamentally, when you really get down to the very small, the universe is fundamentally unknowable. It's fundamentally random. You can determine within a certain variation statistically how things are going to operate, but you can never really actually know the nature of the universe and causality. And this, if people want to really get sort of the extreme of this in terms of the psychotic, there's a movie out called What the Bleep, where it's basically it's
What bleep do we know?
yeah, what the bleep do we know, which is basically an attempt to take the paradox of quantum physics and use them to justify baby boomer sexual fantasies. Yes, I mean, it's a bizarre movie. I mean, it does that. Everything just becomes reality is whatever you want it to be. You can determine reality. It's really just basically determining of the very. We're sort of programmed to go along with one statistical possibility of reality in the movement of matter at the subatomic level. But if we can figure out how to sort of, get beyond how we could choose one of the other possibilities, since there's no real definite way that the world or universe is going to unfold. There's sort of a band of possibilities. It's just a matter of figuring out how to, tap in and determine the one which is going to make you feel best. And anyways.
Yeah.
But it is the essence. It's an attempt to use science to justify and promote the essence of baby boomer culture and ideology. Because really, it's just you. It's about you. How do you feel? What do you want? Reality is what you experience. Reality is what you want. So here's Russell. This is the guy who really set a lot of this stuff in motion. He says, according to quantum mechanics, it cannot be known what an electron will do in given circumstances. There are a definite set of alternatives open to it, and it chooses sometimes one, sometimes another. We know in what proportion of cases one choice will be made, in what proportion a second or a third, and so on. But we do not know any law determining the choice in an individual instance. And I'll just read through, you'll see all these are sort of related to that. Let's see, is this? Okay. There is, however, one aspect of the religious life, and that perhaps the most desirable, which is independent of the discoveries of science, and may survive whatever we may come to believe as to the nature of the universe. Insofar as religion consists in a way of feeling, rather than in a set of beliefs, science cannot touch it. And that becomes a theme of much of Russell's life. I mean, he was your quintessential Gnostic, who believed in a certain empirical, logical, deductive approach to science, but also left open this out that feeling and experience and religious fervor, etc., could never be proven, disproven by science or anything. And so it also has to be given a certain validity and weightedness. And, you can imagine, it's very much, it really also gets at the issue of cultural relativism, right? That there's no truth in culture. That you can't say whether one belief is true or not. Since really nothing is ultimately knowable, can we say there is in fact truth? And so it really is sort of the complete counterpoint to what LaRouche develops in his ideas of economic science, that all ideas can be ultimately measured as to their truthfulness and what is the effect of those ideas, their adoption and action upon, or acting in accordance with, what is their effect on on human population, on the development and expansion of human creativity. You know, we can know the validity of a cultural idea based on what is the effect that that has on a peoples who adopt that idea. Does it increase their power to be creative? Does it expand their notion of humanity, or does it constrict it? So Russell goes on. I come now to the last question in our discussion of cosmic purpose, namely, is what has happened hitherto evidence of the good intention of the universe? The alleged ground for believing this, as we have seen, is that the universe has produced us. Is there not something a trifle absurd in the spectacle of human beings holding a mirror before themselves and thinking what they behold so excellent as to prove that a cosmic purpose must have been aiming at it all along? Why, in any case, this glorification of man? How about lions and tigers? They destroy fewer animals or human lives than we do, and they are much more beautiful than we are. How about ants? They manage the corporate state much better than any fascist. Would not a world of nightingales and larks and deer be better than our human world of cruelty and injustice and war? The believers in cosmic purpose make much of our supposed intelligence, but their writings make one doubt it. If I were granted omnipotence, I should not think man much to boast of as the final result of my efforts. And finally, he says, questions as to values, that is to say, as to what is good or bad on its own account, independently of its effects, lie outside the domain of science, as the defenders of religion emphatically assert. I think that in this they are right, but I draw the further conclusion, which they do not draw. The question as to value lie wholly outside the domain of knowledge. And so that was Russell. And unfortunately, with the death of Roosevelt, with the death of Einstein and others, this is what was left to take hold both in the domains of science and politics. Right? The breakthroughs in atomic physics became the super weapons of H.G. Wells' One World State. The discoveries as to the nature of space and time became now twisted ideas about the arbitrarity of space and time, about the non-reasoning in the universe, and became the foundations and became what they looked at as the scientific justification for baby boomer culture. Relativity, environmentalism, you name it. It's all contained in the way that Russell and then the followers of Russell and the circles of Russell used the breakthroughs of people like Einstein and the breakthroughs in quantum physics to justify a reasserting of the oligarchical ideal and the oligarchical belief system, and particularly the ideas of man. And so we actually see that there's a definite parallel in the domain of science that goes along with what we're investigating with this 32 video. That just as the potential had developed around the Republican notion of political economy, so too are there great breakthroughs and potentials developing in the domain of science and epistemology. And just at the point that died, to a mere flicker with the death of Roosevelt, so too brought the end of that arc of development that started with Riemann leading up to people around Einstein, Planck, etc. And so now this is where LaRouche comes in and saying, look, we have to now pick up that torch. That we have to reverse the 40, 50 plus years of backwards science, of backwards economics, of backwards people and political developments, and revive the tradition of Roosevelt, and then revive the tradition in science of people like Riemann, Vernadsky, and others. And that's in fact obviously what's occurring with the work in the basement and the work in the locals in general with the trunk line, the Kepler, Fermat, Gauss, Riemann trunk line, and really putting our movement and really science, since we're the only ones who now represent this, back in line with that arc of development which produced the greatest discoveries and the greatest potentials for mankind. And so that's where we are, and that's what I can say about that tonight. And like I said, there's a lot of other stuff in in the next couple of weeks. Chase and I'll do some sort of class on, to give people a better idea of some of this stuff with Einstein and relativity and quantum physics and the problems and paradoxes, etc. So, are there any questions?
Cody, how is Nicholas of Cusa's revolution in science different from Riemann's?
Well, Cusa was the one who made the discovery about the transcendental. The idea that there are principles which operate above the totality of their effects. Like with the idea of the quadrature of the circle is that there are principles which are higher that are controlling the experimental domain that you're investigating. The attempt at the quadrature of the circle was to use a certain, effectively algebraic, geometric construct to try and approach the circle. And so what Cusa discovered and put forward was that there was something above that there was something that had a transcendental relationship to the quadrature, to the linear, which was the circular. And he used this as metaphorically, to develop certain ideas about the relationship of man and God. But for science, what that meant was that there was no longer did we in effect have to be bound by the algebraic. That there was something higher than the algebraic, which was the transcendental. And that the transcendental was characterized by a type of change in the circular, for example, in the planar, which was of a least action quality, which was of a principled quality, was reasonable. So the thing about the circle in terms of planar figures, it's the only one which is, as LaRouche develops, which is self-evident. Its nature is reason for its existence, because its very nature is of a least action quality, is reasonable. You don't have to assume anything to justify a circle's existence. It's kind of, you don't have to assume anything to justify the existence of the good in the universe. Right, God is good, and therefore will create that which is good. And so, so what you have with the transcendental is an investigation of that kind of a phenomenon. And so with what Cusa developed and is picked up by Leibniz and others was getting at the idea that beyond the domain of the sensually perceptual and the measurable are principles, and that those principles will express themselves or be expressible as least action type phenomena. Or, there's various ways you can put it. As certain kinds of compounded circular actions, so to speak. If in planar geometry the circle is the one self-evident least action form, well, we're starting to move beyond simple planar geometry and think about higher spaces. Well, those higher spaces are going to project themselves as multiple connections of least action phenomena.
Multiple connections of least, like the the way you would generate a circle on a plane by projecting light into a sphere?
Well, not this, but more of what's the idea behind a circle? And then looking at that, how does that? I mean, this is what people like Gauss and others were looking at: was how does when you're dealing with something like two principles or more operating simultaneously, how does that express itself as one form? Well, it's going to be a form which is characterized by a relationship, a multiply connected relationship of least action phenomena. But all this was set off by Kuza, and saying that you could only really know the circle and understanding the transcendental quality of the circle, that you can never get to the circle from a lower species. In the linear, the quadratic, I mean, it's not quadratic, but the linear figure, the many-sided polygon represents a lower species than the circle. Right, the circle can generate those polygons, but those polygons can never generate the circle.
Right.
And so he introduced that concept of the transcendental. And that becomes the basis if you just, you look at what Fermat did with his principle of least action, what Leibniz did, what Gauss did, what Riemann did. They're all expanding the development of this transcendental phenomena.
So, but more specifically to the political attacks, Riemann was more specific to Euclidean definitions and axioms and postulates. And then, were you saying that Kuza is he's leaning towards what specifically? Like, what is he?
Yeah, he's leaning towards the same thing. It's just, as is often the case, a certain potential has to be developed before someone is able to fully express the totality of the truth that's being investigated. But don't get caught up in a sort of better or worse kind of thing between Kuza and Riemann. It's not.
No,
It's not like Riemann is better than Kuza and Kuza somehow failed to do what Riemann did. It's just, it was a different time and he's looking at a different phenomena. Well, not a different phenomenon, but it's just he existed as a different potential than what Riemann did.
Yeah.
But it's one, in a certain way, it is part of a one. If you look at some of LaRouche's ideas on the simultaneity of eternity, the minds of Kuza, Riemann, etc., they kind of exist as a one in beyond space-time, so to speak. This is sort of how it unfolds in time. But, it's something to investigate, you play around with and kind of get at. Really try to figure out what is Kuza's revolution.
Right, of
All right, I got a question about geometry, or this notion of geometry specifically.
Mm-hmm.
LaRouche in chapter 5 of So You Wish essentially says something to the effect that the internal and external design of a machine determines if the machine can actually work and how well the machine can work. the internal geometry of the machine.
Mm-hmm.
Like in the case of, let's say, an aeroplane. In the case of an aeroplane, the internal and external geometry or design of the aeroplane determines if it can fly. You know, the internal design being, you know, of raw materials which you compose according to the aerodynamic principles which allow for flight. And the internal design is like combustion for motion, right?
Right.
And this applies for if the machine is mechanical, like the aeroplane, or biological, like the human body, right? And the human body is designed according to certain, you know, geometrical designs. You know, everything is designed according to certain geometrical designs. Of course, the human bodies is much more elaborate. We got the central nervous system and all of this, which allows for thought, right? And all these higher things. Well, okay. Now, if you take geometry in that case, or in those examples, let's compare it to like a flute, right? A flute. You design a flute. This is simple design, and it's used to blow, or if wind passes through it, it makes a sound. Now, in the case of the flute, would that be a good analogy for how these individuals are looking at geometry, or I should say, is the notion of geometry expressed in physics what is the notion of geometry expressed in physics? I should have just said that and not said that whole thing. I didn't know, but what is geometry? The notion of geometry is expressed in physics. What is that notion of geometry? Or how has the language evolved to, you know, begin to express and be able to do such phenomenal things?
Mm-hmm. Well, a lot of it is that you're looking at a geometry which corresponds to the way, the quality of change that occurs in the physical domain you're investigating. That the geometry, in effect, becomes a certain kind of a mental image of, it's a mental image of the isolating of a part of reality. To try to give you a way of figuring out the internal characteristics of that reality. That you're trying to, you know, for example, you're looking at a certain kind of, you're investigating a phenomena. And, you know, like this example that I don't know, you've maybe heard this simple, I don't know if it's a joke or what it is, but this discussion about, you know, if you start, how does it go? Right, if you start in a position and it only takes you 3 90-degree turns to get back to that same position, where were you?
Where you first started?
Yeah. Like if you, I guess really only 2 90-degree turns. Like if you start somewhere and you're able to travel, you set off in a direction, right? No. You start somewhere, you move in a direction, and then you take a 90-degree turn and move now in that direction, and take another 90-degree turn and move in that direction, and you end up back where you started. So the 2 90-degree turns return you back to where you started. Where did you start?
first 90-degree turn.
Yeah, but what I mean, if I go this way, right, and I turn 90 degrees, and I go this way, and I turn 90 degrees, am I ever going to get back to where I started?
Not necessarily.
Yeah. If you're on the Earth.
Okay, well, if I'm on the Earth, right. If I'm on the North Pole,
Yeah.
right, and I go, whatever, and I go, I head in a direction, and I go 90 degrees, and then I go 90 degrees again, I'm back to where I started. So, now, I can't, if I'm actually on the Earth, I can't see what kind of surface I'm on geometrically, right? When you're on the Earth, you can't really see that you're on a sphere. And some people say, well, if you're on the horizon, but that really doesn't tell you you're on a sphere. But say I conducted an experiment where that phenomenon occurred. Now in your mind, you can start to develop an idea, well, what kind of geometry corresponds to that as a reality? Right? I conducted a physical experiment where 2 right turns return me back to my same position. Now in your mind, you might develop a geometry of a sphere. Right? Okay, a sphere is capable of producing that same kind of effect. And so now you might start to investigate all kinds of characteristics of the sphere as a way of understanding the kind of physical phenomenon that maybe you were investigating with that experiment. And that's the kind of relationship you're looking at with geometry and physics. Is that you're looking at certain kind of phenomena and you're producing certain kinds of changes, certain kind of paradoxes, right? Now, if you have in your mind some idea of the kind of geometry of the space that you exist in, and something paradoxical now occurs in reality, that means that the geometry that you've developed in your mind about the shape of the space you live in is not fully true, right?
You know what's funny? The only reason why I understand what you said, even remotely, is because of the work I did on your honest Kepler. That makes sense from that standpoint. You got the inequalities. It's like, damn, what's creating this?
Right.
And so Kepler shows you, he recreates the actual geometry, which would actually make those
right
visual inequalities.
Right,
now,
exactly.
It seems like a gigantic leap between Kepler and the A-bomb. That's a big ass jump right there. It's like you're looking at the stars, inequalities, then you get the slit experiment and shit. You passing particles through shit. So that's a big jump.
Well, not really.
I mean, how does it change? Like when you get into like that content.
Well, because it's like, I mean, like he's saying, he's the better of them, like Moon and others, are taking the same kind of investigations that Kepler did, but now into the very small. I mean, just to give you a sense of this, you've heard obviously the famous thing of I equals mc squared, right? Energy is mass times speed of light squared. Well, a lot of that develops out of his investigation of the fact that as mass moves with a velocity, it gains energy. And so out of that, he's starting to look at, well, what if something were to move at the fastest light, it would actually gain an infinite amount of energy.
It would be big as the universe.
Well, but that's the question. It's not necessarily a question of size. Mass, you can have...
Massive as the universe.
Yeah, I mean, you can have... two things which are very different size, but if I got a dumbbell and I got a big old bag of feathers, the feather looks like it's bigger, but doesn't have much more mass, right?
Yeah.
So he was looking at the fact that, okay, you've got these very small particles, photons, etc., that are traveling at the, close to the speed of light. Now, even though their mass is very small, they're going to have a high amount of energy. And now, what if you get a bunch of these? What if you set off a chain reaction where you've got millions of these things moving, where, in effect, it's like something smaller than you can think, right? A very small atom moving at that speed. It's like getting hit by... It's like something that small having the mass of a freight train, but still with that size.
Yeah, like a bullet.
Right.
Or like a grenade.
Right. Which, why, I could...
Like an atom bomb grenade.
Yeah. So, I mean, it was, in simple sense, that's what he was looking at, was that, well, you could actually create a phenomenon where you're able to produce a tremendous amount of energy with a very small quantity of material. Because you effectively have, a small amount of material with initial mass, and you're accelerating it to, near speeds of light, and producing tremendous amounts of energy. And then it was a question of figuring out how do you actually create the conditions to do this. And what they found is that, certain kinds of highly radioactive material, what reason it's considered radioactive? Because it's decaying. It's actually naturally shooting off parts of its substance. It's decaying, what they call like a beta decay. So it's actually losing material, protons or whatever. Now, if you get a bunch of that material and you set it up in a configuration, what's shot off of one is enough to shoot it up to hit if it hits another one. So I've got another nucleus here, and here's a nucleus, and a little piece shoots off this one. It hits this one. Its velocity, its energy is enough to break the bond that's holding this nucleus together. So now this thing splits and it shoots off pieces. And if you set up the configuration right, you set up a chain reaction to where these things are shooting off and breaking off. This one, it's shooting and breaking off ones around it, and you're just, you're releasing this massive amount of energy.
Reactionary energy.
And then it just becomes a question of setting up the geometry in such a way that it's either controlled or, if a bomb, it's not really controlled. It's just set it off. But with a nuclear reactor, you're using the configuration of geometry such that it's controlled, such that it's only, you're only breaking up a small amount at a time so that you're releasing energy, but not all of it at once. It's not like the whole thing is, so you get a lot of heat. And then that's harnessed to drive steam turbines and all kind of stuff.
And that's what y'all gonna be doing in next basement crew.
I don't know if we'll be doing that.
Releasing atoms in the basement and shit. Releasing neutrons. No, but what type of like work is gonna be like the advanced geometry of Riemann and Einstein and stuff?
Yeah, I mean I don't know exactly, but from what Lynn has said, it's going to be looking at the later works of Riemann.
Yeah.
Whenever he went to Italy, and really trying to fill out and get exactly an idea of what Riemann was working at to perhaps correct and advance some of the stuff that's being done by Einstein and people around him. So the problem is, a lot of what's happened is that because the epistemology and some of this stuff has been lost,
You gotta create it again.
certain breakthroughs that could be made are not being made in the domain of physics. Like one example, just to give you a sense of some of where the problem lies. You heard the Fusion Energy Foundation.
Yeah, fusion.
There are certain people,
Fusion and all that. Yeah.
there are certain older scientists around, people like this guy Stephen Bardwell, and this guy Wells. They're all dead now. They're old. They're like Lynn's age. Maybe they're even older than Lynn. And they had their problems. These are the guys that Lynn always talks about. Yeah, these are guys who worked on some of like the tokamak type reactors and fusion physics, plasma physics. And these guys, Lynn said their problems were often when they had to go to the blackboard and they'd try and get all sophisticated with the math and then be like, no, just, you don't have to do that. You're trying to fit revolutionary discoveries and ideas into a mathematics that doesn't allow for those ideas. But anyways, one thing, like, for example, Bard, well, I think it was looking at was in these very hot plasmas, looking at these toroidal plasma structures, that you get the formation of these called filaments. Yeah, they were like these vortex filaments, like little tornadoes in there, right? And what he was looking at was that these are naturally forming structures, stable structures, inside the plasma that may in fact be creating pathways, least action pathways within the plasma towards fusion. That in these filaments, certain least action pathways are created to facilitate the fusing of nuclei to produce fusion energy, right? Whenever we went to, what's that place called? General Atomics.
Man, y'all went to General Atomics?
We went down there and we went and saw, the dude showed us the reactor, right? The guy who was the head of they got a tokamak, a mini tokamak down there, where they have the plasma and they're working on fusion. They can actually create they can fuse elements and shit.
Machine while I was there?
No, but they show. Because it would be crazy or something. But yeah, they have their own like generator. And all. But anyways, the thing is that he also said, and he's like describing what they have to do, how they have to use powerful magnets because they pump the gas in, and then they're just like shooting energy into this thing just to make it hotter and shit. It's like 100 times hotter than the sun.
Damn.
And it's just whipping around. This plasma is whipping around this thing, super hot. Right? And then they use magnets to contain it, to confine it, to keep the shape to it so it doesn't just get all wily. So you have to use super powerful magnets. That's why it takes all this energy to contain it. So it maintains this solid structure and is whipping around. The idea is that the stuff gets whipping around, these things start crashing into each other and fusing. They're like, right? Now, what he said, one of the things he said, but in this process, some of the stuff we have to look out for is you get these filament formations, these little vortexes, and so we're always trying to make sure they don't develop. We're always trying to smooth them out and this and that. So he's trying to get rid of the exact same thing that Bardo and others are saying we want to actually investigate and try to produce more of, because they might hold the key to more efficient fusion. So, it's just sort of an example of kind of, even though there's certain advanced research going on, some of the tradition, epistemology, and the way of looking at it has been lost to where, they may not be looking where they should be looking and trying to get rid of stuff that might actually be what they want. So anyway, I think the idea is to advance things up to the point where we can start reshaping the institutions in the right way.
Yeah, so you saying the epistemology of fusion energy is dead?
Could very well be. It's teetering on the edge of extinction.
Oh yeah, we hear it, right? Damn.
So that's what we're doing.
We went to the fusion reactor in Seattle.
Yeah.
It's a sphere Mac.
It's a sphere Mac.
One of the sphere one.
Did they turn it on?
No.
I think you could watch one of them. They use them.
It costs like $20 million or something to turn it on once. They have like 20 gigazillion watts to do it one time.
Isn't that why they shut down? Isn't like that the main argument used to?
Yeah, that it costs a lot of money to start it.
It's too much energy to produce.
Yeah, just to get it going, it's like you need like another nuclear. But the same thing happens with the sphere, man.
All right.
The outside's going one way, but on the inside, you get to a certain point, it's going. It goes a different direction.
Right.
In the middle.
Huh.
It changes direction.
Right.
It's creates a different type of vortex.
Right. Huh.
But they were actually trying to figure it out up there. They weren't.
Right. That's tight. Where's that? It's in Seattle?
UW, yeah,
Really?
they have one.
Huh. Yeah, that's tight. That's the problem, though, is that if things get too far out of control, you're not producing scientists anymore, you're just producing engineers. An engineer is very technically proficient with the accepted laws in mathematics, but they're not really experimenting or pushing the boundaries, or they don't know how to think about it. They just know how to apply the accepted knowledge in maybe new and creative ways, but you get stuck.
How does the cold fusion process work? Isn't it like they create this like bubble and they collapse it fast as hell, and then like smashes in on itself?
I don't know. I don't know much about the cold fusion. I mean, I've read it, but I don't know how it works. I think recently Lynn said something about it, like he clowned it or something.
Like it's bullshit.
Yeah, no, it's just like he thought maybe people were just too ready to jump on it, trying to make money or something within our movement. Something like that.
Yeah, because the dude that actually did the experiment, they made this whole documentary that discredited all of his experimentation. And they showed bit by bit. As a matter of fact, they took a whole team of scientists and on the documentary showed you, like, page for page, like, every part of his experiment was just fraudulent.
Right.
Yeah. I was like, man, this shit is slandering fusion energy.
Well, I mean, there may be some to it, there may not, but I just remember Lynn said something recently where, I don't even know, Lynn made, I don't know if he necessarily said cold fusion's a fraud, but it was something where he just was like, yeah, people just tried to jump on it too quick, without really knowing exactly what was happening. The people in our movement jumped on it too quick to try to make a buck off it or something.
Interesting. When y'all going in the basement? Y'all going in the lab?
June, end of June.
June. Yeah. Damn. Who's all gonna be in there?
I think Aaron Halevi and
Lady, yeah, who else?
Ohyang and Megan Rollard.
All right.
And then Sky and Peter are going to be there.
Damn, Sky and Peter doing a double tour. Damn.
They got Stop Lost.
Peter gonna come out like Moses and shit, like. Damn. That's what's up.
All right.
Everybody's coming back to each other.
Man. The lady in the basement. Damn it. My boy Aaron is gonna be Aaron and Moses. Man.
Want to do that thing? What?
The thing.
We're gonna do the thing. You know,
What's the do that? Whatever. Anyway.
man. You know what? I don't understand though. I don't understand. Like,